everyone, this is Poornima Deepthi working as an assistant professor in the Department of ECE at MLR Institute of Technology. So today's my presentation is about a programming using 8051 microcontroller. So this video is a part of series microprocessors and microcontrollers. Some of the basic programming of 8051 has been already explained in the previous video. Before watching this video, do watch that video also. So coming to the overview of today's presentations, so how we will write the simple programs to compare two bytes of memory or the data present in memory, and how to write the subroutines by using 8051 microcontrollers, and how to scan and how to multiply the data if any loops are there. So how we will be executing these such type of subroutines or scans and comparison operations. So coming to the first program, here the statement of the first program is we need to find out how many equal bytes are there between two memory blocks. So obviously two memory blocks is there. So we need to compare each memory block with the other memory locations of the other memory block, and we need to find out how many. So we need to find out the number that the bytes of those locations matches. Right? They have already given the location address also. So here two memory blocks 10H to 19H and 20H to 29H. So these two are the memory locations. Let us consider these two are the memory locations. This was the first memory location and this is the second memory location. So now see how many memory locations are there. So obviously it is from 10H to 19H. So it is at a hexadecimal representation. So how many will be there? So it will be 10. 10 memory locations will be there. So from this is for 20, 21, 22, 23, 24, 25, 26, 27, 28 and another one which is nothing but 29. So total 10 locations are there. Here also there will be 10 locations, and you need to compare every one location with the other location. If it matches, we need to keep it track of matching bytes. So the second location will be second location and the third locations that's carry out. So how many times this comparison operation need to perform? So it's obvious there are 10 locations in the memory 1 and there are 10 locations in the memory 2. So 10 locations, 10 comparisons, right? So we need to keep it in a loop that the comparison will be operated for 10. So that's why here in the case of R7, I'm taking the count actually 10 decimal, right? 10 decimal is equivalent to the A in the hexadecimal. So that's why I'm keeping R7. So R7 is used to keep the count, how many times the loop need to be executed. So coming to the next one, move R0, 10H. So we can't compare the two numbers in the memory itself. So we need to move that particular data in that particular memory through using the registers. Here the registers I am using to transfer the data from the first memory location. So I am loading 10H address to the R0 register. So now R0 register is having 10H address location. And as well as R1, I'm taking the second memory location. So R1 is loaded with the 20H address location. Here now move R6, 00. Why I'm making the R6 register? I'm making actually the R6 register empty. Why? So here in this particular R6 register, I'm using this R6 register to store the output. So the output should always start from the 0 because it is a count. That's why I'm making it to clear the previous any values will be there in the R6 register. So I'm making sure that R6 register will be empty to get our output properly. So that's why R6 register is having 00H value. Now all the inputs have been taken. So now I need to take the content from the location and I need to compare it. And if there is match, I need to increase the R6 register. If not, I need to decrement. Like that I need to perform. So let's see what I have already written. So here move A, R0 indirectly mentioned that the content of the address location present in the R0 need to be moved to the A register. Here the content, the address present in R0 is 10H. Suppose here 12 and here 21 is there. Like here 13 and here 13 is there. We will see. Okay. Yeah, so now in this particular case, what it will become, the here R naught is having 10H address location. So the data present in 10H address location is 12, right? So A register is having the value 12. Now I need to take another location value into the A register. So memory to operations will always be performed by using the accumulator. That's why I am always copying the data in the A register to the another general purpose register, which is here is a B register. So here the B register is also having 12. So now again these two has done. Now the data present in R1 location. So R1 is holding the value 20H. So the data present in 20H location is 21, and that is moved to the A register. Now I need to compare these two registers, right? So that is the thing. We need to compare. If it is equal, then we need to increase the count. Here now see CJNE. CJNE is compare and jump. So it is a conditional loop that I have already explained in the previous videos of branch instruction. So here it is a conditional loop that if the condition satisfies, then the controller need to move to the address specified or the label specified in the instruction itself. So here it is CJNE is compare and jump if not equal. So if both the numbers are not equal, that means the condition will satisfy and jump to the loop. What is the label? So if A and B, we need to compare these two, the data present in those two registers, and if both of them are equal, then it need to jump to the location no match label. So here no match label is there. So the controller need to execute from here. Okay, so let's see, 12, 21, it's not equal. So obviously it will, the condition has satisfied and it will move to the no match label. Here what I have written, so increment R naught. Yes, here what I have written, increment R naught. So now I have already compared to the first two locations of the first locations of two memories. So now I need to check this in the second location. That's why here I am incrementing R naught. Now what is the data register present in R naught? So R naught is having 10H. After executing this increment operation, it will become 11H. Likewise here increment R1 operation is done. So increment R1 means, so R1 previously it is 20H, now 21H. So this second 13 and here also 13. These two will be get compared. Okay, before that we need to decrement the R7 register because we have already kept the count there 10. So here one comparison is already done. So we need to decrement the comparison. That's why one instruction they given. What is that instruction? Decrement and jump if not 0. Okay, so now we need to decrement the register present there. So here the value of R7 is 10 in a decimal, so A. So it will be decremented. So what is the value present in R7 register? It will be 9. So no, the condition doesn't satisfy because decrement and jump if not 0, right? If it is not 0, then it will jump. So no, it condition satisfied, it is not 0. So the condition will send the instruction, the controller need to move to the location next label. So here again, so here the process will continue. So again R0 value, now the locations is 11H and 21H. So the R0 value 13 will come into the B register, and again this 13 will come into the A register. Now both of them are equal, right? Yes, when comparison is done here, if yes, both of them are equal. Here what is the condition? Compare and jump if not equal. No, here the contents are equal, so this condition will not be satisfied and the controller will execute the next instruction. What is the next instruction? Increment R6. So as I already told you that R6 is the output. So now R6 equals to 1. Again this loop will be executed unless R7 equals to 0. If R7 equals to 0, then the next instruction would be the exit or end instruction. So this is how the 10 locations will be compared, and if how many of the equal numbers will be there, that will be represented by using the R6 register. So this is how we will find out if both the values in the different memory locations are equal or not, okay, or same or not, right? Yeah, coming to the next program. Here they have given same the block of 100H to 200H. See, so here they have given 100H to 200H. So what is the difference? We need to find out. So we need to keep loop, right? So we need to find out actually how many locations are there in between 100H and 200H address locations. Okay, now they are telling find out how many bytes from this block are greater than the number in R2. So the value should be greater than R2 and less than number in R3. So it should be less than R3, right? So store the count in R4. So we need to find out the range. So one largest number is there and two numbers are there. So we need to find out the numbers between. If the memory is having the number of locations in this 100H to 200H, we need to find out how many numbers will fall under this condition. There is two limits they have given. So suppose I can take from R2 to R3. So how many numbers are there in between these two loops? I need to find out. So I will keep this as the lower limit and this as the higher limit. I need to check whether the number present in that memory location falls under this condition or not. If it satisfies this condition, this limit, then the output will be incremented by 1. So at last of the comparison, we need to find out that yes, how many numbers are within the range or not. Okay. Yeah, this is the thing. First we need to find out how many times this comparison operation or how many times this every location of data we need to check. So how we will calculate the count? So here the locations we need to find out. So 100 to 200 means, see, 200H to 100H, right? So how many, what is the difference? So there is 100 locations. This is actually the hexadecimal number. So if we want to find out the actual locations, we need to find out the decimal equivalent of this 100 number. So what is the decimal equivalent? So we will find out like 16 power 0, 16 power 1, so 16 square. So it is 256. So the locations is 256 locations. So it will start from 0 to 255, right? So we need to, so first location we already will write. So we need to keep how many count? 255. So what is the hexadecimal equivalent of this 55? 255. So the hexadecimal value of this 255 is FF, the highest value of the hexadecimal 8 digit. So or 2 digit 8-bit binary number. Okay. Yeah, that's why here if you see here I kept here I kept R7. So this is used for the count or loop purpose. How many locations I need to check, and here I have given the location, starting location. So if this is the memory, so 255 memory locations will be there. So this is the starting location, right? Yeah. So 100H I have given into the DPTR. Why we are giving to the DPTR? See here, if the internal memory, if we are using the controller's internal memory, then only 2-digit locations will be there, right? But here they have mentioned the 3-digit locations, which is of a they mentioned so 12 digit. So it's always telling that it is the external memory locations, so not in the internal RAM locations. This present in the external RAM location. So how we will communicate with the external RAM locations? We will be using always DPTR, data pointer, to hold the external address locations. That's why we are giving this 16-bit address location to the DPTR. Okay. Yeah, so R7 is used for the counter loop 250 times, 255 times. Now move R4. So we are keeping output in the R4. That's why I'm making sure that it doesn't have the previous value. So I'm making it clear, right? Yeah. And if move 20H comma R2, so I am keeping the lower limit. This is the lower limit and this is the higher limit. I am storing 20H in the address location. 20H I am storing the lower limit and 21H I am storing the higher limit. So now the data present in the DPTR, first byte will be moved into the accumulator. Here why I am using move X instruction, because at the rate DPTR means it is the external operation. So to specify that external operations, I am using move x. X will represent it is a external operation. So the data present in the first location of DPTR, which is nothing but 100H location of data, will be moved to the accumulator. So I need to check it with the lower. First I am checking with the higher limit. If it is satisfies the condition of higher limit, then it will go to the lower limit, right? Yeah. So here CJNE means compare and jump if not equal. So if both the numbers are not equal, so now I need to check for the lower limit. So compare and jump if to the the location, the first location data will be compared with the higher data. If both of them are not equal, then it will move to the lower label. So here the lower label is there. So now here it need to check. So what it need to check? Jump if no carry. See, when comparison operations are going on, if A and B, comparison between these two numbers, if A greater than B or A equal to B, now in both conditions carry flag will be 0. Okay, if A less than B, then only the carry flag will be enabled. So because the comparison operation in 8051 will be done like this, A minus B. So if the A is having the greater number, A minus B always will have the normal value. So carry flag, borrow will not be there. So carry flag will be 0. If both of them are equal also, we will get A minus B as 0, right? So carry flag will always be 0. There is no borrow. But while using A less than B, so here it is telling B is greater than, so there should be the borrow to subtract this. So while we are using any borrow, then carry flag will be 1. So I am checking now this condition. If carry is not there, then the number is greater. So lower, the digit lower limit, the number actually present in that thing is actually the greater than the lower digit. So that satisfies the condition over here. So here, yeah, here I was checking that if it is not no carry, jump if no carry is there. So jump if no carry means, so it will not fall under the condition. So out, so it will go to the then it will be incremented. Next DPTR will be incremented. So the first one doesn't fall under the limit, so it will move to the next location. It will check this location. Now see, if the location, the data is actually, yes, the data is not equal to lower, so its condition satisfied where lower limit is satisfied. So sorry, upper limit is satisfied. So now I need to check lower limit. So if here JC out, here jump if no carry is there, no if there is no carry, let's consider that no carry is there. So now, so yes, so the number is greater than the upper limit, lower limit, so it will fall under the condition. So here I need to check compare and jump if not equal, number is not equal, then it we need to check limit. So JC out, if carry is there, then increment R7. So the particular number present in that particular location falls under the condition. So I need to consider the count as 1. That's why increment R4. As I already told you that R4 is used to store the output. So how many times this loop will execute? Here see, DJ, decrement and jump if not 0. If R7 is not 0, first I need to decrement the R7 register where FF will become FE. If it is not 0, then it will execute the loop next again. So until unless the memory locations, all the 255 memory locations will be scanned and the output will be automatically get into the R4 register. So there we need to find out. So this is how we will check each and every location of a memory and using these limits. Okay, yeah. And coming to the next program. So here the crystal frequency is given as 12 megahertz. Actually the crystal frequency where 8051 is actually operated is 11.0592 megahertz precisely, but here they have given that that particular controller is working on the 12 megahertz crystal frequency. Okay, so I need to make a subroutine that it will generate delay of exact 1 millisecond. So I need to write the program to generate delay of 1 millisecond. Use this delay to generate square wave of 50 Hz on pin number 2. So pin 2.0, that particular pin need to provide like this. So square wave I need to produce. So the delay between this is how much? I need to produce 1 millisecond. So usually while providing this delay, we have a separate unit in 8051, that is timers unit. But here in this particular thing, the thing is we didn't covered until now timers. So without timers, how we will be creating this delay, and we will see how, if using timers, we will generate the delay in the next coming videos. So here we need to, there is a clear cut location that we need to find provide the 1 millisecond delay. So how we will provide that, we will see. And the 8051 requires, for one machine cycle, it requires 12 clock cycles. Okay, so if to provide one machine cycle, it would require for 12 clock cycles. Okay, let's see. So here move R6 comma 0 AH. As you all know that 0 AH means it is a 10 in the decimal. So why I am keeping 10? So we will see. So here delay program called, a call delay means absolute call. There is no condition. If that a call is there, so this delay will be executed over here. Okay. Yeah. So what in here I was creating that 0FA. So what is 0FA? So FA means 16 power 1 and 16 0. So here 10 and 16, right? So F means also 15 into 16. So what is the value? Actually it is 240 plus here it is 10. So 250. So I am keeping 250 in R7 register. Why? I will explain here. So for NOP, as I already told you in the previous instructions, that NOP is no operation. It is used to just kill the time of the controller, right? So here to execute this NOP operation, actual time of the controller is 1 cycle. So here another NOP operation is there. So how many times? Here 1 cycle and here 1 cycle, totally 2 cycles of time will be generated over here. Here decrement J and Z, so it will be decremented. So now it will become 249. So how many times this loop will execute? This loop will execute completely one time, and here this loop one time. Totally 4 times the loop will be executed, right? So 4, and here how many what is the value of the loop? That is 250. So 4 into 250, how much? Right, 4 into 250, 1000 cycles. So what is 1000 cycles? Here 1 cycle is 1 microsecond. So 1000 cycles means 1000 microseconds, which is equivalent to 1 millisecond. So here if I want to execute this loop, I can provide 1 millisecond. That is the question, right? Yes. So that's why I am making here clear PEEP 2.0. So usually when we are using ports, the default value in ports are all 1. So it is always be the input ports. So that's why I'm clearing after 1 millisecond the ports will be cleared. Again it will be loaded with the 10. So 10 times it will be executed in row 10 milliseconds. So it will produce 10 milliseconds a call delay. This is how we will generate 1 millisecond of delay in the programs without using the timers. If we are using the timers, it will be different. Okay, coming to the next program, and here what they told, continuously scan port 0. So I need to check port 0 values if the data is other than FF. So if data in the port is not FF, okay, so I need to write a subroutine that will multiply it with 10H. So whatever the data present in the P0 will be multiplied with the 10H decimal value, and I need to send that particular output to the port P1. Okay, so I need to continuously monitor P0. If the data present in P0 is FF, then again monitoring will be continued until it finds the other data. If any other than FF, if any data is there, so that particular data need to be multiplied with the 10 decimal value, and the output will be loaded into the port P1. Alright, okay, see. So first of all, I am just making it P0 is FFH. So if it is FFH, then no problem. So what now I'm moving the data in the P0 to the A register. So now I need to check compare jump if not equal. I need to compare the data present in A and 0FF. So if both of them are equal, and if there is equal not equal, then it will send to the loop, so that there we need to multiply. Here in this case both of them are equal because the port is having FFH, so comparison operation will say that both of them are equal. So if this condition will not satisfy, so it will move to the next location. What is that? S jump. S jump means small jump within the range, so it will go to the loop again. So I already told you, no, so if the data is FFH, it is continuously monitor until unless it finds the other data. If this line is not there, so we need to check that, we need to take the value of P0 here. So if P0 value is FEH, not FFH, okay. So now what it will become here, compare and jump if not equal. Yes, both of them are not equal, so this condition satisfies now. And where the controller need to go, the controller need to execute the loop labeled with the data DAT. So here, so what here, a call multi. So here also multi loop is going to execute. What is the multi loop? Move b comma hash 10h. They have mentioned it will be multiplied with the 10h, so I can't multiply directly, so that's why I'm making 10h in the b register. So now the data 10h will be moved to the b register. So already the data present in the P0 is moved to the A register. So FE is in the A register now, and it will be multiplied with 10. So the output will always be stored in the A register according to the multiplication and division rule in the 8051. So now I need to move the data in the output. That output need to be moved to the which port? Port 1. So that's why move port 1 comma A. Return. So it will be returned to this loop. So S jump again, it will move to again and it will load. So this will be continued until the new data, if any new data is, this will be continued until we disturb the controller itself. Okay, yeah. So until now I have discussed how the comparison operations can be written and how to compare and how to check if the number falls in this particular loop, in the particular limits, and how many times these subroutines can be executed to provide, how can we provide delays in 8051 without using the timers unit, right? And how to scan the data continuously present in any one of the ports or any one of the loops like that. Okay, thank you.